Hey AP Chemsters, this is Mrs. Vanderlooy bringing you 8.8 Blank Wall. This is the last section for the periodic trends, and the last one is all about electron affinities and metallic character. So what is electron affinity? Well, I can say I have an affinity for chocolate, and what does that mean? It means I love chocolate, okay? So electron affinity is really the loving of electrons, and how does that manifest itself in the elements? It's, well, which element will have the greatest amount of energy released when it gains an electron. It's like saying, yippee, I got some chocolate, or yippee, I got an electron. So it's the energy change when the gaseous atom, needs to be gas, gains an electron. Most often it's energy release. So the most loving element for electrons will lose the most energy. And the question is why? Well, we're back to Coulomb's law again. Remember our buddy Coulomb? The Coulombic attraction between the protons and nucleus releases energy. It's like it's snapping together, okay? So here I have the neutral chlorine, and it gains one electron to make the chloride ion. And look how much energy is released right here. A lot of energy is released, 349 kilojoules per mole. That's a pretty big amount. So the trend here, again, this is all about trends, periodic trends, not a predictable pattern, in general going down a group. Rule of thumb, but not 100%, is that the electron affinity is going to go down as you go down a trend. But going across a period, the electron affinity becomes more and more negative, or in other words, more energy is being released. Your exceptions will be your noble gases. They do not want to gain an electron, okay? And some alkaline earths are positive. And the question is why? Well, for the noble gases, let me screw around here. For the noble gases, all right, Ng, okay, think they have a filled octet, okay? So look at helium, 1s2. Do they really want to gain another electron and get out of this filled octet to have, you know, a non-filled octet? Because if they gain one, it's going to go in the 2s, and it is, you know, you've ruined your octet. Well, I guess helium doesn't have an octet, but I think you get the idea. As far as the group 2, the alkaline earths, here let's use, I don't know, beryllium, 1s2 and 2s2. If you gain another electron, you got to go into the 2p shell. So now you have, here's where you gained an electron. You're starting a whole new shell again. You're losing that stability of a filled shell. So that's going to, you have to force it to take it, okay? Your group 1s won't be so bad, because if you have a, let's say lithium, 1s2, all right, and a 2s, if lithium gains one, hey, now you have a filled 2s shell, which isn't too terribly bad. And so lithium, even though it's a metal, it will tend to lose electrons. It's not as bad of a deal to fill your 2s shell as it would be to have to start a whole new shell again. Okay, so hopefully that makes sense. Metallic character. What's going on here? Metals will lose electrons. So what trends would indicate a metal losing electron? Well, hopefully the biggest one is ionization energy. Isn't that the definition? How much energy does it take to lose an electron? So as you go down a group, the metallic character does what? It increases. Why? Because it's easier and easier to rip away those electrons the further they are away from the nucleus. Think of your Coulombic force again. As the radius between the outermost electron and the nucleus is bigger and bigger and bigger, it's harder, or sorry, it's a lot easier to rip away that electron, so it becomes a greater metallic character. As you go across the period, the metallic character goes down. Why? Because you have a greater effective nuclear charge, so you have greater attraction, so it is harder and harder to lose that outermost electron. Okay? Let's go. Hopefully you recognize this problem. This came from section 8.7. I've already done this, so let's go to the next page. All right, so on the basis of periodic trends, choose your more metallic elements from each pair if possible. So tin or tellurium? Well, let's find out where they are on the periodic table. Okay, so here's tin and here's tellurium. Okay, so which one is more metallic in character? They're in the same period. So again, metallic character means you're going to lose electrons more easily. So if I want to lose electrons, I want to have the lowest amount of attraction. So which one has the lowest amount of attraction? Which one has the lower effective nuclear charge? The effective nuclear charge for tin is 4 and tellurium is 6. So this one is going to have lower effective nuclear charge, less attraction, therefore easier to remove the electron, therefore a greater metallic character. And as you think about it, you think of tin being a metal too, don't you? Tellurium, you probably don't know a whole much about tellurium, so maybe that answer makes sense. What about the next one? Okay, so what about phosphorus and antimony? Let's go back and look at our periodic table again and check this one out. Okay, here's phosphorus and here's antimony. So again, we're thinking about which one's going to be easier to remove the electron. They're in the same group. So they have the exact same effective nuclear charge of 5, so that doesn't really help. So now we got to think about the distance between the outermost electron and the nucleus. Antimony has 2 more shells than phosphorus does, so those outer electrons are further away from the nucleus. And again, as Coulomb's law states, that the energy required, there is inversely relational to the radius, so that if you have a greater radius, it takes less energy, and so antimony is going to more easily give up its electrons. And hopefully that makes sense, because phosphorus, as you know, is a nonmetal. And if you think about this, there's my staircase. Antimony is on the metallic side of the staircase. It's actually considered like a metalloid, but it is on the metal side of that staircase. So hopefully that makes sense to you, that phosphorus being a nonmetal, antimony being a metalloid, that it does have more metallic properties than phosphorus does. So the answer should be clearly antimony. What's the next question? All right, germanium or indium? Let's look at the periodic table again. Germanium and indium. Okay, hopefully this is a fairly obvious thing. There's 2 reasons why. Again, we're in this kind of a diagonal, which really shouldn't be too conflicting here. So the effective nuclear charge of indium is 3, germanium is 4. On that alone, we can say, well, there's less attraction between the electrons and the nucleus because of the effective nuclear charge. What else can we say? Indium has 1 more shell than germanium, so those electrons are also further away. So between the 2, it should be very clearly indium. All right, and kind of like go back and look at this again. All right, remember that? Germanium is a metalloid, indium is clearly a metal. So hopefully all that makes sense to you, but the main reason is indium has a lower effective nuclear charge, therefore lower attraction to the outermost electron, and it has 1 more shell, so it's further away, less attraction, easier to remove. Okay, let's see what the next one is. All right, so sulfur or bromine. Take a look at the periodic table one last time. All right, here is sulfur, and here is bromine. Oh, I don't like it when a diagonal goes that way, because which one's going to win out? This has an effective nuclear charge of 6. This one has an effective nuclear charge of 7. So if I'm just looking at that, I'd say sulfur. However, bromine has an extra shell, so it is further away, so it's inconclusive. What should we do here? I'm going to look at something real quick. Okay, I want to look at the first ionization energy. So sulfur would be, I believe, right here, and bromine, I believe, is right here. So if I look at just that alone, which one is easier to remove? It looks like it is sulfur in that case, and instead of bromine, it takes about 1,000 kilojoules per mole to remove the electron from sulfur. It is about, 1,200 to remove from bromine. So only on the basis of looking at the actual data can I really predict that. It is conflicting as far as the effective nuclear charge or the period, if you will, that in this case it is the effective nuclear charge wins out. It's really awfully close to tell, and unless you're really going to look at the data, it's really hard to say. So let's go back here, and pick sulfur. Okay, so in this case, the effective nuclear charge is going to win out. I don't think the AP will ask you that. I'm not going to ask you that. I can certainly ask you one of these three, and there shouldn't be any issues. Number 4 is kind of a mean question, isn't it? So it says arrange the following elements in order of increasing metallic character. We have silicon, chlorine, sodium, and rubidium. Well, hopefully you can figure this out. So why don't you try that on your own and then see what you get. So pause this, figure it out, and come back. All right, so I hope we got rubidium being first because these are in the same group. Rubidium's further down, so it is easier to get rid of its electrons. Then here's sodium, definitely a metal. So what do I do about silicon and chlorine? They are in the same period, so this has an effective nuclear charge of 4, this has 7, so silicon has less attraction, easier to remove, and then chlorine with the greatest effective nuclear charge is going to be the greatest. Okay, so that concludes 8.8, and that's it for now. Don't wait to be great.